To my channel. Today we shall be looking at this technical coding interview question: minimum depth of binary tree. And the question says, given a binary tree, find its minimum depth. The minimum depth is the number of nodes. That's an important number of nodes. That's the count of nodes along the shortest path from the root. That's another one node down to the nearest leaf node. A leaf node a leaf is a node with no children. So like here, 3, 9, so 1, 2. So that's why we have 2, because that's the shortest. That's the shortest part. And here you have 2, no, 3, no, 4, no, 5, no. The shortest part is 5 if you draw the graph. Okay. Whenever we have problem like this, there are like 2 or 3 things that we have to keep in mind. Number one is we have to first of all establish the base cases. So we need to know the base cases first. We have to get the base cases right. That's the first thing. The second thing is we have to ensure we are using recaution on sub problem and a sub problem. Going to use recaution and a sub problem. Sometimes the third one will be, sometimes we may need an helper function if it warrants so. So those are the 3 basic things we should keep in mind whenever we have this problem. So let's deal with the first part of the problem. The first part is the base cases. So what are the base cases we could have? Number 1, case 1 is what happens if we have a tree that does not have a root. So if the root is null, that's the first case. So what do we do in that case? What will be the count? Automatically that should be 0 because there's nothing to count. So we can handle it. So if not root, then what do we return? We return 0. Okay, that does that. The case 2 is we have only roots. That means we don't have anything on the left or the right of the root, so it's only root. In that situation, what do we do? In that situation, we return just what? The count, which is 1. So if root, if it is only root, so we return 1. The other case again is, now we might have root, but we only have the left and we don't have the right. So if we only have left child, so case 3, left child only. So if we have left child only, so in that situation, what do we do? Left child only. So what we do is we want to definitely get the minimum from, so let's say we don't have the left child, then what it means is we have to get the minimum from the right child. We have to get the number of nodes, the minimum depth from the right part of it. So we check that if not root dot left, okay, left child only, that means if not root dot right, sorry about that. So we have only left child only, we don't have anything on the right. So if not root dot right, what do? We have to make a recaution on the root dot left. So we have to call back our function again. So we call back main, so we say self because it's in a class, main depth, and we call it on the left. So we call it on the root dot left, because we know we don't have right, and that is what we're going to be returning. But there's a caveat there, is that before we can make a recursive call on the right, we must have counted the root node, which is 1. So we must have counted the root node. So in that scenario, let's say we don't have this side, so it's only left child we have. So left child only. So if you have only left child, so sorry. Yes. So if you have only left child, so we don't have anything here. So we first of all have encountered this root, so we need to count the root as 1. Then we now have to make a recursive call on the left here. We have to make a recursive call on the root of left, that is on this one. Similarly, if we have the next case, which is case 4, if we have only the route child only, then the reverse works. So we say if not root dot left, that means we don't have root of left. We just return, we make a count of the root, which is 1, then we return self to make a recursive call on main depth of root dot right. That will just be opposite of that. So that is case 4. Now the final case is when we have the 2 children. So we have case 5, when we have both lefts and right child of the root. So the root has both left and right child. In that situation, definitely we have to call the 2. We have to call this, because we have to go on the 2 sides. Did it paste that? Oh, sorry. We have to call this. So we need to call this. And we also need to call this one too. So the 2 has to be called. We need to call this. So what do we return? What we return is the minimum of the 2. So we return the minimum of the 2. Whatever gives us the minimum. And that's it. So we're already doing the recursion on the sub problem. So these are the sub problem, because we are now looking at the left of the root or the right of the root. The same thing here. So that's it. Recursion is difficult to work through. So our time complexity, in the worst case is when we have a linear, an imbalanced tree where we just have only maybe a right node or a right child in a linear fashion. So in that situation, the time complexity is going to be linear in the worst case. So if we have a linear tree, so the time complexity is going to be bigger of the height, whichever what the height is, the height of the tree. So where h is the height of the tree. Okay. What about the space complexity? Space is constant. We are not using any extra space, so we have big O of 1 power space. Alright, so that does it. So let's say we just have not, it returns 0. If we have only 3, it checks, okay. We only have root, so it returns 1. Okay, This may be wrong, so we need to check that there is no left and there is no right. So this is wrong. So here will be the if not root dot left. So we make a basically say and not root dot right. That is, we are guaranteed that there's nothing on the left of the root and there's nothing on the right. So that is only root. So because we just say if root, then there could be things on it. So this we guarantee to just give us 1. Here, if there's no right, okay, there's no right, so we just go to the left. Then we have a cost of 1 because we count this first node and add it to whatever it gives us on the left recursive call. Last one is if there's no left, so we only have right, and with the same thing, a cost of 1, and we go to the right and take recursive call on that. And if we have both, and we make a recursive call on both and return them. So let's run it. That gives us a wrong answer. What could be wrong now? Output 1, expected 2. Oh, the same way here we're supposed to say 1 plus. Sorry about that. We're supposed to say 1 plus, just the same way we follow this. So we're supposed to add 1 because we have counted the roots before we go to the left and to the right. Okay, that's trickish. So that works. So let's try the other one. Copy this and see what gives us. So let's run this too. Okay, that too works. So let's submit and see what we have. Good. All right. Thank you for listening and see you in the next one.